All right. So, since we're talking about the beginning, all right, the absolute beginning of everything, all right, we're putting a date to that we went through yesterday during yesterday's class. I said, how old is the universe? I got a variety of answers that came from Google. 14 billion years is the objectively achieved date for the universe, okay? 14 billion. Whereas 13.8 billion, sure, have a seat right over there. 13.8 billion years ago is when our galaxy, okay, got its start, all right? So the universe is a little older than the galaxies, all right? And when I say galaxy, it's pretty much galaxies, all right? And it is estimated that there are 100 billion galaxies in the observable universe. 100 billion, okay? Each with 100 billion stars on average. Some are a little smaller, some are larger, but on average, about 100 billion stars per galaxy, and there's 100 billion galaxies in our observable universe, okay? So 13.8 billion years is this big number that we say that the galaxy is. All right. Now, our planet Earth has a date of 4.6 billion. All right. So these are big, when you say billion, those are big numbers. But I want you to just kind of look at those numbers for what they are. So the difference between 4.6 billion and 13.8 billion is about 9 billion years. Okay. So the galaxy is 9 billion years older than our sun and any planet in it, including Earth, okay? There's 9 billion years. Let's get back to that. So what do we do? All right, for those of you watching this, you may have been here while we went out to the bike rack, or maybe you weren't here today and you're watching it at home. We went to the bike rack as a class, and we measured the temperature of a bicycle tire valve, the stem where you put air into the tube, before we added air and after we did about 10 pumps from a standard bicycle pump size. We measured the temperature to compare. Who can tell me what they were? Because I forgot. Go ahead. You forgot to. Go ahead.
One was like 90.6 and the other was like 97.6.
There you go. There you go. 90.6, 97.6. All right. The temperature went up, and you'll see the video, it'll be there exactly what it was, but the temperature went from lower to higher, an increase in temperature, increase in energy. Now, that little demonstration was a demonstration in thermodynamics, okay, the transfer of energy from one medium to another. So what happened is, the air, the gases that are in what we call air, oxygen, carbon dioxide, xenon, fluorine, all kinds of miscellaneous gases, when we put that pump up and down, it pushes the air through a valve that gets it into a little tube, and then forces that tube into another valve, and every time that you're going into another valve, it's reducing, okay? The aperture, the opening is smaller, so the air is pressurized, it's put under pressure. That's kind of the key here. When we put a gas under pressure, it created heat, all right? We just saw that, all right? So keeping that in mind, all right, I'll have to kind of juggle around a little bit. Put a pin in that. Okay, so we said that, and this is kind of jumping towards what we've already talked about, that we as human beings, Homo sapiens sapiens, have descendants, have ancestors that are not Homo sapiens sapiens. Okay, and we only discussed the Australopithecus. So there's Homo habilis and Homo erectus. There's others. We'll get into those. But early humans, okay, hunters-gatherers, they would, once culture got underway, a patterned way of life that's socially transmitted, once culture got underway and a person in a group, tribe if you want to call it, you are a hunter, you are a gatherer, you are this, you are that, everyone's kind of got a job to do. The hunters, okay, were sort of gauged on how good they were based on their eyesight. And so at nighttime, long before the invention of electricity, fire was the only real form of light outside of the sunlight. And so, there was not much to do at night. They'd look at the night sky, and a hunter who could see a number of stars, a certain number of stars in a certain spot in the sky, if he could see those stars, then he had really good eyesight, and he was considered, all right, you could be a hunter because you have good eyesight. And so they started looking, early people started looking at the stars and started to kind of, use their imagination, because that's one thing that humans really have, is we can recognize pattern. Our eyes are what they call stereoscopic. Okay, we've got two eyes, and so we have depth perception. I don't know if you ever, like, before you cross the road, you kind of look down, and if there's something coming, you can get a sense on how far away that is because of the depth perception. Okay, that's part of our eye-brain system, is we can see depth. We can also see patterns, and that works out well for when you're a gatherer and you're looking up in the trees and you see there's like a big canopy, is what they call it, the tree canopy, leaves and branches everywhere, but you can see that there's fruit. You know, there's something growing on the tree that's useful, or maybe a predator who's hiding there, you know, a leopard if you happen to live in Africa. Which is a big problem for people in Africa, by the way, like nowadays and historically. Like they wear, I'm going off topic, but they have to wear like a mask on the back of their head because leopards don't like to attack from the front. They like to get you from behind. So people who live there, like today and, you know, into the recent future or the recent past, they have to wear a mask on the back of their head that has eyes and everything painted on it because the leopard thinks that the person's walking backwards, so they won't, you know, attack. But it's a problem. But anyway, you're looking up in a tree and you can see fruit or you can see a predator. That is an advantageous trait. All right, so going back to this whole thing, early people looking at the sky, what's this, what's that, wondering. There's this feature in the night sky, all right, they call it the Milky Way. All right, Milky Way. I touched on it a little bit, but early people noticed this, and it wasn't until, like, I mean, it got named for by different cultures. Like the Romans, they would call it Via Lactea, which is like they had streets. They didn't call them streets; they called them ways. So, and Lactea is milk, so they would say like the Milky Street. And then in China, where milk is a less popular beverage into adulthood, they wouldn't call it that. They call it the Silver River. Okay, so historically, the Milky Ways, there's been this thing like, what is that? You know, nobody really knew. But in the 1920s, we're kind of moving ahead. In the 1920s, well, you know, actually, let me back up. Remember I said Galileo with the telescope? He played a big role in trying to figure out, you know, what that was. It was more observable because if you look at it with the naked eye, it just looks like this kind of like milky color kind of streak across the horizon, and the lights kind of puddle together to kind of make it blurred, and it's a little fuzzy, right? So to the naked eye, you can't really discern what it is. With a telescope, you can see that it's stars. And in the 1920s, there was a debate, okay, on whether or not this was a galaxy. And so it was established in the 1920s that there was a galaxy in there, in that cluster. And then in 1926, it was established even further that not only was there the Milky Way galaxy in front, which we're part of, but there were other galaxies behind it, all right? Basically countless numbers of stars. And then as we move on into, you know, kind of more advanced technology, the Hubble telescope, that's where I get these, you know, these numbers that I'm telling you about, the number of stars and the number of galaxies, all right? But let's tie it all back in together. So early on, okay, 14 billion years ago, all right, you hear this thing called the Big Bang Theory. It's a great show, by the way, Big Bang Theory. The Big Bang Theory is basically the premise, the idea that the universe is expanding, okay? That the universe has been expanding since the moment the bang occurred, and that it's been expanding ever since, all right? And what I'm gonna get to is that when you look at these galaxies that we can now see, okay? So there's galaxies that are observable from where we are, that we can measure that they are moving apart from one another. And if you can discern that they are moving apart and measure the distance that they're moving apart, well, that would mean that they were closer together yesterday than they were today. And they were closer together the day before than they were yesterday and the day before. So every day that you go backwards, they were you know, closer together. So you can do a calculation, all right, to say, all right, well, at the rate of expansion, all right, if you were to go backwards in time, rewind the clock, everything in the known universe is in the same spot at the same time 13.8 billion years ago. So that is the, you know, basic, you know, principle for that the universe is expanding, and that, you know, these galaxies are moving away from one another, all right? So when we did our little experiment, we can determine that matter under pressure is hot, okay, heats up. Now, taking what we now know of like modern science, you know, the particle accelerators and all the work from the Manhattan Project and, you know, nuclear fission from the advent of the atomic bomb and all the research and work that's gone in to that, we know that the higher the temperature, the more simple the elements will be made. All right. So what I mean by that is when you look under like a hadron collider, which is the particle accelerator, and you see what happens to atoms when they collide at high speed under high temperature, etc., you start to get a sense of how they behave. And if you take the knowledge gleaned from that, from our experiments, and you take everything that we know up to date, we can sort of paint a picture about what has happened, how we can say this with certainty that, you know, the Earth is at the age it is, and that the universe is the age it is, etc. Okay, so early on, let's not talking about our sun or our planets. Early on, the oldest stars that are still around today, that were alive closest to the beginning of the universe, you know, 14 billion years ago, they produce only hydrogen and helium and trace amounts of lithium, okay, in their core. So stars produce elements, okay? So early stars would produce very simple elements, okay? The hydrogen only has one proton in the nucleus, okay? So then helium has 2, and lithium has 3. So basically, early stars only produced those 2 main components with trace amounts of lithium. Then, have you ever heard of a supernova, an exploding star? Okay, when a star collapses. So like off topic, right now there's a picture in the observable universe. There's no lack of stars, where we can see stars being born, stars in middle age, and stars dying at any given spot that we look at, you know, from Earth. So we get a very good view of what it is for a star to live out its life. But we don't live long enough to observe it, you know, by ourselves, like in a single lifetime, because, you know, we're only around for around 100 years or so, we said. And this can take, you know, billions of years. Okay, so the point is, early on, when stars, early suns and stars were developing, and they're still around, when they explode, they enrich the area with whatever elements that they manufactured in their core while they were alive. And then those clouds congeal, can make a new star with that extra enrichment, explode after they live out their life, which I said could be, you know, billions of years, and they basically carry that enrichment over to the next generation. So we, as our solar system, our sun has, it's manufacturing elements that are much more complex than early stars. So rocks that the planets are made of are not made of hydrogen and they're made of arsenic, oxygen, iron, cobalt, you know, all these other heavy metals. And that's part of, like, remember that little meteorite that I was showing you? In fact, let me grab that. Sorry. Meteorite, okay? And this meteorite has iron in it, cobalt, and nickel, okay? This particular meteorite is a product of an exploding star, a supernova, okay? As is this planet, and as is the material that makes up every living thing on it, including you, okay? So we are sort of, you know, stardust in a way. When a star explodes, okay, every element on the periodic table is spread out, okay, especially the newer stars like our sun is, and the star that came before our sun was here 4.6 billion years ago. So where we are in our solar system is basically the product of all the enriched stars that came before ours that exploded after they lived their life. So the material that went into making up what our planets are made of, what our sun is made of, what you are made of, what the table is made of, everything that comes from an exploding supernova, okay? Water is a unique thing, okay? Water is not, you know, it's very common, actually. Who knows what a comet is? Okay, when I was 12, 1986, there was this comet called Halley's Comet, and there was no internet, but, you know, television had quite a few channels, not like cable, but a lot, and there was a lot of like, it'll be passing by at this time and you know this part of the sky, and it was a big deal. So when it actually did come around, my whole neighborhood, everyone who lived in the neighborhood was like outside, people lounge chairs, you know, stuff like that, watching it in the sky. And I'm a little 12-year-old kid, I was small, and I'm standing next to some adults that were, you know, big, and I'm standing there and I see it, you know, it's got this long kind of tail to it. It doesn't look real. It's like in the sky, but it just looks kind of fake. It's moving real slow. And the guy, who I don't know who he was, he's like, I guess he was reading or reciting something that he heard on TV. He's like, yes, you know, that tail is actually made up of ice. And I was like, ice? Ice is frozen water. I was like, there's water on that? What? You know, just kind of, that little thing stuck in my head. And then later on, when I was an adult, and I was learning about where comets come from in the universe, I learned this, and this is what I'm going to tell you. So they come from this part of the universe that we call the Oort cloud, named after a guy who observed it, you know, Dr. Oort. You know, guys like to do that. People like to do that, you know, name things after themselves. Hubble telescope, Oort cloud. So anyway, actually Hubble wasn't named by himself. Edwin Hubble, he died before it was, never mind, off topic. So water, okay, comes from comets. Now try to imagine this. You ever see a picture of the moon with like craters in it? I was looking at it last night. It was beautiful, craters and everything. There are craters. What are a crater? It's evidence of an impact, okay? A celestial body in impact, you know, an asteroid, meteor, that sort of thing. There's big craters here on this planet, but we have an atmosphere that's kind of covering it up. You know, plants cover over it, oceans cover over it, wind blows, you know, sediment over it, covers it. But when the Earth was early on in its history, it was just like rock. You remember the rock cycle from 7th grade? You know, lava, magma, remember all that? So it's liquid rock, okay? Liquid rock in the interior is called magma, and then when it comes out, it cools, it becomes lava, or before it cools, it becomes lava. So Earth was just pretty much like a big ball of like magma and lava at one point. Just rock in different stages of being harder, which is called solidification. And then when these impacts started to bring in ice, every time a comet would hit the planet, it would bring in a large quantity of ice. And because the planet was so hot, it would just flash evaporate. Okay, as soon as it hit, the water, the ice would just flash evaporate. It would rise up into the, you know, early version of our atmosphere, condense, cool, come back down as rain. It was still hot, it would flash evaporate. And the more water that was brought here, it started to slowly cool the planet down to where only the outside of it, the outer edge, you know, the crust, was actually becoming harder, okay? Becoming not liquid rock, it was becoming harder. No plants, you know, no nothing on it except small traces amounts of like puddled water, pooled water. Could be a puddle, could be a pond, you know, started to get to where, you know, ocean-sized bodies of water were coming. So Earth kind of got its start 4.6 billion years ago, and it was absolutely different than what we think of Earth for most of its life, okay? And it wasn't until water started to be brought here by impacts from different comets that were bringing it here and then collecting and cooling down the planet that it started to go through some changes to its, you know, landscape, let's call it. All right, I'm going to stop there. Do we have any questions?
Hey, I'm sorry. I need Kayla.